Recall from the last lecture that we have defined various topologies, 3 different topologies on the set of real numbers. So the first one was the standard topology, the second one was the lower limit topology, and the third one was the K topology, right? So we denoted the standard topology as tau standard, tau L was the lower limit topology, and tau K was the K topology. Now the question arises when you have multiple different topologies on the same set, whether it is possible to compare them. So the question that you want to ask is that is it possible to compare topologies on the same set, So for this purpose we shall define some terminology. So let me give a definition. So let X be a set and we have 2 topologies on this set X. So tau and tau prime be topologies on X. Okay, so we have a few different terminologies in this setting. So the first one is that if tau, the collection tau, is a subcollection of tau prime, then tau prime is called finer than tau. Finer is the word that's used here, and tau is called coarser than tau prime. So finer and coarser are the words that we shall use to determine which one is larger and which one is smaller. Okay, so tau prime here is larger and tau is smaller. Okay, so the smaller one is coarser and the larger one is finer. Okay, so we can use directly these words larger and smaller, but the terminology that's used in mathematics is finer and coarser. Now if the inclusion is proper, if the inclusion, this inclusion is a proper inclusion, then tau prime is called strictly finer than tau, and tau similarly is called strictly coarser than tau prime. So when you have a proper inclusion, meaning there are sets in tau prime which do not belong to tau, then we use the term strictly finer and strictly coarser. Now it may happen that tau is not a subcollection of tau prime, or it may also happen that tau prime is not a subcollection of tau at the same time. So in this case we use a different terminology. So if neither tau is a subcollection of tau prime nor tau prime is a subcollection of tau holds, then we call the topologies tau and tau prime incomparable. Okay, so incomparable meaning they cannot be compared, and otherwise we call them comparable. And comparable otherwise, meaning that either this holds or this holds. Okay, so so these are the various terminologies that we will use to compare different topologies on the same set. So for example, just as an example, you can consider the two-dimensional plane. Okay, so two-dimensional Euclidean plane, Euclidean space, or the plane. Okay, so in this plane we can define two different bases. So let me call B1 to be the collection of circular regions in R2, circular regions in R2, and B2 is the collection of rectangular regions in R2. So first of all, why are these two bases? So I'll just give a visual intuition for why this is true. So for B1, so we have let's say, first of all, any point in R2 is contained in a circular region. Okay, so property 1 is satisfied for the definition of a basis. So the only thing one is to check is property 2. So if you have two circular regions, B1 and B2, and you have a point X here, so this is the point X, then of course you can take a very small circle, this is B3, which is inside the intersection. Okay, so and it contains X, so X is contained in B3 is a subset, which is a subset of B1 intersection B2. So this is a basis, B1 is a basis for a topology on R2. And similarly you can have for the collection of rectangular regions, again property 1 is satisfied because every point in R2 is can be enclosed within a rectangular region. And for property 2, we can have for example, let's say two basis elements, two rectangles, B1 and let's say like this, B2, and of course let's take a point X in the intersection of these two sets. And again, it's visually clear that if you take a small enough rectangle that contains this point, then it will lie completely inside the intersection. So again here this is B3 and X belongs to B3 and it is a subset of B1 intersection B2. So now these two bases B1 and B2 generate topologies, let me call tau 1 and tau 2. So suppose, so let tau 1 be the topology generated by B1, and similarly tau 2 be the topology generated by B2. Okay, so we have now two topologies, and the question arises, first of all, whether are they comparable, and whether tau 1, and if they are comparable, so if yes is tau 1 finer than tau 2 or coarser. Okay, so we have these two topologies, tau 1 and tau 2, and we want to determine which one, first of all, whether they are comparable, and second of all, if they are comparable, which one is finer and which one is coarser. So again, if you take a visual proof for this, so I claim that they are comparable, and in fact they induce the same topologies on R2. Okay, and for this we will use a theorem which allows us to determine if two topologies are given on the same set, which one is finer, which one is coarser, by looking at the basis elements. So the theorem we want to use for this is the following. So suppose that B and B prime are two bases on the same set X, and they generate topologies tau and tau prime respectively. So B generates tau and B prime generates the topology tau prime. Then I say that tau is coarser than tau prime, so tau is coarser than tau prime, which is just this inclusion tau is as a sub collection of tau prime. If and only if for each x in X and any basis element in B, so B is remember that it generates the topology tau, right? So if you take any basis element B containing X, so this basis element B contains X, there exists a B prime, a basis element in the second basis B prime, such that X is contained in B prime and B prime is a subset of B. So let us see a proof of this theorem. Proof. So suppose first that tau is coarser than tau prime, and we have to show that for each X and B in B containing X, there exists a basis element in B prime which contains X, and it is a subset of the basis element B. So suppose that X is in X and B is a basis element such that X belongs to B. Okay, so how do we find this B prime is the question. So notice that B already belongs to this topology tau, because we have seen that every basis element is an open set by the way we define the topology tau from generated from the basis B. It is easy to see that any basis element is already an open set, and B belongs to tau, and tau is a sub collection of tau prime. So this implies that B belongs to tau prime. Okay, and because it is an open set in tau prime, then this implies from the definition of the topology tau prime as generated from basis B prime, that there exists a B prime in B prime such that X belongs to B prime and it is a subset of B, which is exactly what we wanted to show. Okay, so the forward implication is proved, and now let us look at the reverse implication. Okay, so we know that for each point X there exists and a basis element that contains it in B, then there exists a basis element in B prime which is a subset of that basis element B. And now we have to show that tau is coarser than tau prime. So let us take an open set U in tau, and we have to show that we will show that that this open set U also belongs to tau prime. So since U is an open set, this implies that there exists, given X in U, there exists a basis element B in B such that X belongs to B and B is contained in U. This was our definition of tau from the basis. And now because we already have assumed that given a basis element and a point inside it, there exists a basis element in B prime, which is inside B. So there exists B prime in B prime such that X belongs to B prime and it is a subset of B, but B is also a subset of U, right? So this implies that given any X in X, any X in U, there exists a basis element B prime in B prime such that it contains X and it is inside U, and this is equivalent to saying that this set U is in tau prime, and because of the way we define it again. So it's just using the definition to show this theorem. So now that we have this nice criteria to determine which one is coarser using the basis, let us go back to the example of B1 and B2 that we defined for circular regions and rectangular regions, and try to use this theorem to show which one is coarser than the other. So for example, if you take a point X and a basis element in B2, so a rectangular region containing X, then it is obvious that we can take again a small circular region containing this point X, which lies in the interior region of this rectangle. So this is B1. Okay, so this means that the topology tau2 is coarser than tau1 from the theorem 5.1, which I described below. And similarly, you can also reverse this process and you take a circular region, say B1, and take a point X here, X. But again, it's quite easy to see that we can cover it inside a rectangular region. This is B2. So we have reversed the roles of B1 and B2, and this implies that tau1 is coarser than tau2. And so taking these two together, this means that tau1 is equal to tau2, and so this means that B1 and B2 generate the same topology, on R2, and these topologies will be called the standard topologies. Standard topology on R2. Okay, so just as we defined the standard topology on R, this is the standard topology on R2 on the plane, and this is the one that is most commonly used. Okay, and now we will go back to the various topologies that we defined on R. So I'll just go back to the first page where we had the standard topology on R, the lower limit topology on R, and the K topology on R. And the question arises, the question that we asked in the beginning was that whether it is possible to compare these topologies, and the answer is in the following theorem.